How you doing? I'm Mr. Rose. As you can see, we're back in the dungeon, and today we're going to start talking about current, resistance, and EMFs. This should be chapter 5 in your text. So all of you have probably done some circuits before. You should know some key buzzwords. You should know things like series circuits and parallel circuits, resistance and currents, and EMFs or voltages. We're going to take all that, we're going to put it together to get our understanding from, way down here to hopefully somewhere up here or even off the screen. So to start, we're starting with current. Well, all of you probably already know current from a rudimentary class. Current is just the flow of electricity. It's what we've always used it for. So here I have a zoomed in version of a wire. I've taken a cross section here and I'm adding some current in that, some electricity in it. Well, if I make a slice, take a cross section, so I'm going to take a circular slice out of that wire, so I'm looking at the cross-sectional area, and I'm going to label that cross-sectional area A, try not to knock my board over, and if I want to count the exact number of, say, charge carriers, I'm going to be very specific to only say charge carriers, going past that cross-sectional area, what I'm going to see is I'm going to see the exact number of charges that go by every second. By definition, that's what we call our current. We are calling our current or a charge per unit time, or it's a coulomb per second, and we measure that in amps or amperes. Well, to be exactly more specific, we're going to say that the number of charge carriers, that's just going to be N, and it's going to be those number of charge carriers that I have moving. And E is just going to be the charge of my charge carrier. Now I have very important here, we are not using electron current, we're using conventional current. Now this does confuse some students because we know that electrons are actually the things that are carrying the charges. However, we use what's called conventional current. What conventional current is a positive charge flow. So basically an electron is swimming upstream like a salmon. If I have the current going this way, that is my charge carrying flow. Electrons are actually swimming in the opposite direction. So we're only going to be talking about conventional current, basically a positive charge flow. So moving on, taking my wire, put my wire over here. And now I want to know, say, how much current or how many charge carriers are passing through a specific section in a given amount of time. Let's just say 1 second. Well, to do that, I'm simply going to take a specific length of this wire that I labeled L. I'm going to take that exact length of wire. I'm also going to say that is the exact length of wire that my charge carriers can travel in 1 second. So essentially L and V are the same thing in this case. Well, I know my wire could vary in size. I could have a small wire. I could have a big thick wire. So I can tell you that the current is equal to N, those number of charge carriers, times the volume of my wire. This is basically just the cylinder. So the volume of that times my charge carriers. The charge of my charge carriers, rather. To get this volume out of there and put it in terms of velocity, I can just say that my current is equal to the area times the velocity times the number of charge carriers N times my charge E. Now, current flow, contrary to what a lot of people think, is not linear. In other words, it is not just an electron that hits an electron that hits an electron that hits an electron going this nice linear path. Electrons are bouncing all over the place. If I could get a better marker than this one. These electrons, some go that way, some go that way, some go that way, and their motion in the wire is actually completely random. So we can't just use this nice linear model that we've used before. What actually turns out to be a little bit of a better model is something that we call current density. Well, we know what density is. We've used mass density before. You know what density of an object is. Current density is the same thing. Current density is just current divided by area. Well, I know current, N times my E times V. I know current, A, V, N times Z divided by area, so my area goes away. So now my current density, J, which is a vector, is my number of charge carriers, N, times my charge of my charge carriers, E, which is typically the charge of an electron or proton, 1.6 times 10 to the negative 19th coulombs, times the velocity those guys are going. Now this works nice and neat, package it up in a nice little envelope as long as current is uniform. Luckily in wires and circuits, current usually is uniform. Otherwise, we would have a random range of current flow. Light bulbs wouldn't work well, cell phones wouldn't work well, we'd all be lost. So If the current, however, is not uniform for whatever reason, so I have some arbitrary shape. If the current is not uniform, my I current is going to be the surface integral. So I have this random shape. Basically, I'm going to take all these little patches, and I'm going to measure the current that's going throughout there. So I'm going to take the surface integral of my current density, J, times my surface area, dA. This is not very typical. I just want to show it to you so we have some completeness around this topic. So the question I have for you while I change boards, why does the current actually flow? So before my editing magic, why does the current actually flow? We know inside of a conductor, there's no electric field. We know that as a fact. However, that's only if the conductor is ideal. We don't live in an ideal world. So let's say I have this copper wire. Inside that copper wire, I have current flowing. Well, why do I have current flowing? I have current flowing because there's an electric field inside of my conductor. Mind blown. Why is there an electric field inside my conductor? Because even though it's a conductor, everything has a different amount of conductivity, which is the next thing we're going to talk about. So it's not a pure 100% conductor. There is some resistance to it. So if I didn't have this electric field, like I said earlier, these electrons, they're just going to go in some random motion and not really have a desire to go anywhere. They're going to be bouncing around all over the place. Once I have this electric field set up, contrary to popular opinion, electrons traveling in a wire don't go very fast. In fact, they actually move relatively slowly. They actually start drifting in the direction of this electric field. So my current density, J, is equal to NE times V, where N is the charge, the number of carriers, E is my charge, V is the velocity. That V is actually my average velocity. So how do I figure out this average velocity? Good place to start, or I shouldn't even say why is the average velocity. I should say what's making this move and how is the velocity related to that electric field. A good place to start is always where we started before. Newton's second law. Newton was a really smart guy. So we know Newton's second law, the acceleration is equal to a force divided by mass. If there's an electric field, there's probably an electric field due to some electric force, which is what Coulomb told us. So I know the electric field is equal to, this used to be Q times E, but now I just have this as an E as my charge, or my charge carrier times the electric field. So I can say the acceleration is equal to E times E divided by m, my charge times my electric field divided by m, and that gives me an acceleration, which means all of those electrons in here are going to accelerate forever and ever. And if I go back to my current equation, current is the area times the velocity. Well, if they're accelerating, that means my velocity is increasing, which means my current isn't steady. So right now it seems that I never have a steady current because I have a constant acceleration inside of my wire. Now we know that can't be true. Why can't that be true? What's going on here? What topic am I missing? What I'm missing, gave you a minute to think there, what I'm missing is the fact that the wire is not perfect. So inside the wire, the electrons are making random collisions at no particular time interval, no consistency. They are going straight, hitting one, hitting one, hitting one, all over the place. So I'm looking for an average velocity, and because of that constant collision, the objects obviously can't accelerate. Every time there's a collision, there's a new force, which means accelerate in the opposite direction. So to find this average velocity now, we're actually looking for the velocity in between collisions. So I'm going to say my average velocity of objects in between collisions is some velocity at time 0, which I'm just going to arbitrarily set to 0, plus the velocity at some time t later. Well, I know that acceleration of my object is E over m, which is my charge carrier electric field divided by mass, times time. That gives me my velocity from, well, you can't even see me. That gives me the velocity. We're going to arbitrarily set to 0 now, plus my acceleration times time, where I've labeled this ti. Now that ti is the time in between successive collisions of one electron to another electron. This ti is come to known as a tau. So we know the average speed, or the drift speed, so to speak, of my electrons has to do with my electric field, the charge carriers, the mass, which is just the mass of an electron, times this time constant tau. Now that tau is an average time. we actually can't calculate this so well. There needs to be some quantum calculation to do this. This is a little bit above our pay grade, so right now we just kind of need to take that as fact. Now what I want to show you here is putting everything together. If I put everything together, we know that current flows when there's an electric field inside of a conductor. Now that electric field, so to speak, is due because we're applying a potential difference, which we can get to over here. So once I get that electric field, I know my charge carriers are going to drift in that direction of the electric field, like I just drifted across the screen. So once I'm drifting in the direction of the electric field, I'm going to undergo these random collisions. Well, if I'm undergoing random collisions, I don't want each individual velocity. I want the velocity over the entire time scale. So I have my current density, J, number of charge carriers times the charge times my drift velocity. Plug in my drift velocity, we find out that J, my current density, is equal to the number of charge carriers, N, times E squared times tau divided by mass times that electric field. Now I want you to think about this equation. Does this equation make sense? Well, remember, current density is just current I divided by area. So if I have more charge carriers, N, will I have more current? Yes. If I'm inversely proportional to mass, if there's a bigger mass, are things going to move slower? Yes, that also makes sense. Let's skip over the E squared tau. If there's more time in between each successive collision, will my average velocity, or will I be able to move faster? Yes, because I'm going to have more time. I can get up some more speed or carry more momentum. The electric field, without the electric field, I don't actually start to drift. There's no reason for me to move. So yes, and this E times my electric field, that's giving me the force to move. Now this was E squared. So that E squared, where's that second E? Well, this is kind of counterintuitive. It's almost self-proportional. Current needs those charge carriers. So without those charge carriers E, I can't have any current. This formula does make perfect sense to us. Let's move up here now to talk about the materials. Well, we talked about resistivity or resistance. Well, this sigma is something that we're calling conductivity. I take all of these numbers down here, and I can relate that. Number of charge carriers, E squared divided by M times tau, that is the conductivity of my material, and that changes per material. Copper has a different conductivity than silver. If I take that back into my charge density, I can simplify my charge density to say that charge density is just sigma times the electric field. Or now I can really see what conductivity is about. It's not really about the material. It's a ratio of charge density divided by my electric field. Well, if there's something that's called conductivity, that means there's probably an opposite of that, which is resistivity. Resistivity is just the inverse of conductivity. So it's a ratio of the electric field divided by my current density. So we can kind of put that together and say my electric field is my resistivity times my current density, or we can say it's my current density divided by my conductivity. Now let's make sense of all of this. Go back to my original wire. I have a wire of length L. To get my electrons to move, I am going to need to put a potential difference to that wire. We know that potential difference, let me get out of your way here. We know that potential difference is due to the electric field. Other way around, we know the electric field is due to the potential difference. So I'm going to say my current, this is nothing new, is my current density times A, which is equal to sigma my conductivity times my electric field times A. Let's just regroup things so I can look at it a little bit different. My current is equal to sigma conductivity times area. I'm going to replace my electric field with my rudimentary definition of an electric field, a potential difference per length of volts per meter. Right, so if I have a potential difference to this wire of length L, my electric field is volts per meter. Now grouping everything, I should notice I have sigma, A, and L. Sigma's conductivity, and that depends on the material. A is how big my wire is, the cross-sectional area. L is the length of my wire. These three factors are factors that affect the resistance of the wire. If I have a longer wire, it's harder for electricity to get through. If I have a material that's not as conductive, it's harder for electricity to get through. If I have a small cross-sectional area, it's harder for electricity to get through. Those three things are related to this resistivity constant, or just simply resistance. This is Ohm's law. Ohm's law, the current is equal to the potential difference divided by the resistance, where resistance is given a unit of an ohm. to tie that into resistivity, I can see that resistance is equal to L divided by sigma times A, the conductivity times my area, which means the resistance is equal to rho resistivity L over A. Let's put all that back together, what we just saw. I can say resistance is equal to rho L over A, where I know that rho is just my inverse of conductivity. So my resistance is also equal to L divided by A times 1 over sigma. All of this kind of ties everything together into a nice, neat bow. Please feel free to like, comment, and subscribe. That's all I have for you today. Please don't resist this too much, and enjoy the rest of your day.